Hi guys, today we're working on 9.1c, finding equations of sine waves. We're just furthering our study of understanding trigonometric functions, the graphs of trigonometric functions. Okay, so today we'll work backwards from the graph to the equation. So our essential question, how can I use the graph of a sine wave along with formulas for amplitude, period, and phase shifts to write equations of sine functions? Okay, and so here's how I'm color coding. Amplitude will be in red, period will be in blue, phase shift will be in green. And let's start with some formulas because we need them if we're going to be successful. So let's start with the definition of amplitude. So an amplitude, and I'm going to just zoom in here real quick. Can you give me a definition of amplitude? What is the definition of amplitude of a sine wave? What is it? Describe it. Go ahead, Spencer.
The distance between a function's midpoint and its peak.
Peak. So you're saying it's vertical, right? So it's the vertical distance from the midline, right? To a maximum or a peak. And what's the formula for amplitude? The absolute value of A. Okay, so we definitely need to know what is amplitude, what does it mean, and what's the formula of the absolute value of A. All right, let's switch to period. Can someone please explain to me what's the period of a sine function? What does that mean, the period of a sine function? Do you guys remember? It's measured, go ahead, Alexis. One full revolution? Can be, unless there's some transformations happening. The distance between two peaks or two valleys, right? So it's horizontal. So it's the horizontal length of one full cycle of the periodic function, right? It's a periodic function. So over one period, you'll see a full sine wave or you'll see a full cosine wave, and then the pattern just repeats. So period, how do we find that? What's our formula? 2 pi over absolute value of B. Okay, so there's our definition and our formula. Then I'm going to switch to my green pen. I did say green, right? Okay, and let's talk about the phase shift. What is the definition of a phase shift? A phase shift of a periodic function. Horizontal shift, right? It's just a push the graph left or right. What's the phase shift? And how do we find the phase shift? What's the formula? Opposite of C over B. Okay, so those are our formulas that will be really helpful because today we will be searching for what is A, what is B, what is C, and in these formulas you see the letter A, you see the letter B, you see the letter C. So very helpful to work for those theorems and those formulas. Another important thing to talk about is the distance between 2 points. How do we find that? And today we'll be looking for some horizontal distances, or we'll be looking for some vertical distances. All right, definitely we'll be looking for some horizontal shifts. So we're going to be looking for horizontal distances or vertical distances. So just to keep it simple, we'll just do x sub 1 minus x sub 2, the absolute value. Always absolute value because we're looking distance is always positive. And of course, if we were doing a vertical distance, y sub 1 minus y sub 2. But I think that you guys won't really need to do that because you can identify amplitude pretty quickly. All right. And the other thing that I would like to mention is you remember the other day that we would start with when we were trying to perform our phase shifts and our period changes at the same time. We'd take the period of a sine function or a cosine function, which was 0 less than or equal to bx plus c. Notice that I'm talking about the b and the c, less than or equal to 2 pi. We did use that often to find our phase shift and our period change at the same time. So we can also rely on this formula to help us identify B and C. So I'll show you two alternate ways to do what we need to do, and that will be something we will employ. All right, so let's take a look at these two problems here and talk about the conditions that have been set so that we get the correct equation. Because I do have to tell you this, I could write a cosine equation for that. Don't you think? Doesn't that look like a cosine function? Or a sine function, right? And this could be a cosine function I can write for any cycle in the cosine function that I want. How I could shift the phase left 10 pi over 2 if I want to, or right 18 pi over 6. No, not maybe 15 or something crazy like that. I can do that. So we are set with some very, very strict conditions so that we will all get the same equation as an outcome. Okay, so let's read the problem. It says the graph of an equation is shown in the figure. Find the amplitude, period, and phase shift. Okay, so we'll have to do that. We'll look at the graph and we'll identify those things. We'll use colors to do that. Then write the equation in the form of y equals a sine of bx plus c. So we're going to specify that we're working on the sine wave, not the cosine wave. All right, and here are the conditions. A must be greater than 0. So that means A has to be positive, because it has to be greater than 0. B has to be greater than 0. So that means B has to be positive. And then the least positive real number C. So C has to be, sorry, green. C has to be a positive real number 2. And so that's the smallest possible positive C, which means when I'm looking at this graph here, if it's a positive C, is it pushing my graph left or right? Left, right? If it's a positive C, we go the opposite direction, left. So what this means right here, the least positive real number C, is the shortest shift to the left possible. The shortest, the smallest shift to the left. So if maybe you want to write that over here as this is the smallest shift of a sine wave, which starts at the equilibrium, goes high, hits the equilibrium, goes low, and then comes back up. So it's the smallest shift left of that pattern, because we want the C to be positive, and we want it to be the smallest C possible. So the smallest shift of the sine function to the left, that's the explanation. All right, so let's take a look at our picture. I'm going to grab my red pen, and the first thing I'm going to do is identify the amplitude. It's always the easiest one to find. So the center line, would you agree the midline is the x-axis? So we're looking at the distance from the x-axis to the peak. And so what is our amplitude? So our amplitude is 2. So that means that our A is 2. Right? And it has to be a positive A, so we can't say that it's a negative 2 amplitude. Right? Can't say that. All right. Now, let's find our B term. So in order to do that, so we found our amplitude, it was 2, and now we know what our A is. So let's work on our period. So the period of this specific graph, and if you don't mind, I'm going to zoom in just a little bit so that I can point some things out. So let's take a look at this graph here. So if I'm looking for a sine wave, and I'm going to like focus on the sine wave just to the left of the y-axis according to our conditions, could this be a starting point? And then up to a peak, back to the 0, hit the trough, back to the 0. So would you agree that that is one cycle of a sine wave? And it's the shortest shift left of the sine wave that's possible, because it usually starts at 0 and does that. Okay, so what is this value right here? Let's look at the scale. Here we have a scale from 0 to pi, and that's been cut in half. So every tick mark is a half. But we're looking at this value right here, which is not quite at the pi over 2, and this value right here, which is not quite at the pi over 2. Would you agree that if I do this, and I do this, and I do this, that that's 3 equal distances, the pi divided by 3? Yes? So this would be 1 distance left. So would you agree that it's probable that that's a negative pi over 3? And then to here would be the distance pi over 3. Okay? So we have 1 full cycle of the sine wave, 1 shift pi over 3 left, right? So let's find the distance between those 2 points. So the distance of this, we'll just call that our x sub 1, and we'll call this our x sub 2. Negative pi over 3 minus pi over 3. The absolute value of that is negative 2 pi over 3, or 2 pi over 3. So there's the period of one sine function. So, okay, so we know the period is 2 pi over 3. So we found that. Now, how could we use that to find the value of b? We know the full period. We want to find b. John, what's your suggestion?
The equation for the period is 2 pi over 3.
So, okay, so 2 pi over, and since our b is positive in this case, do I have to put the absolute value? No. So 2 pi over b equals, go ahead, continue.
B is the denominator, so the denominator of that is 3. So that's b. Right. So 2 pi.
I think you're right. So we found that this actual graph has a period of 2 pi over 3, and the formula for period is 2 pi over b, so b equals 3. And so we get that data there. That's really interesting and helpful information. And now the last thing we have to do is identify the phase shift per the instructions, and then find our C term, and then we can write the equation. So I'm going to switch to my green pen, and I'm going to look at my phase shift. The smallest shift left possible is a shift left, and I'm going to use my green pen here with a little arrow. What's that a shift left of? Shift negative pi over 3? You agree? All right, so the phase shift is negative pi over 3. All right, so we've done task 1. Amplitude, period, phase shift, all determined off of the graph. Now let's find our C term. Now remember, the formula for phase shift is the opposite of C over B. And in this case, our B term is 3. So the opposite of C over 3 is equal to negative pi over 3, because that is our actual phase shift. So we should be able to use those values to identify that C equals pi. And you can see it, and you don't have to actually solve the equation that you created for pi, because you can see that that would make the left side equal the right. All right, so let's write the equation. Using our A, B, and C, which is our overarching goal here, can we write the equation fit to those specified conditions? So y equals 2 sine of 3x plus pi, close parentheses, and there's the equation. Now, remember that I told you at the beginning when we were writing out all the formulas that we could use that whole phase shift period change idea at the same time to find our B and C terms, because don't you agree it takes a little time to find your period and phase shift, right? So if I were to just come over here and say, okay, here's what I know about my period with my phase shift, for the shortest shift to the left possible, was we started at negative pi over 3, was less than or equal to our value of x, less than or equal to pi over 3. That was our final period change with the phase shift. So what I'm thinking is, since I'm working backwards from the graph to write the equation, that I could just write this statement working backwards. Do you agree? I want to make the left 0 and the right 2 pi. So what would I do first? Multiply all sections by 3. All right, so that's negative pi less than or equal to 3x less than or equal to pi. Do you agree? That's just multiplying the entire thing by 3 so we can clear the fraction. Now what? I want this to be 0. So I did my multiplication, so now I have to use my addition. Right? I would have to add pi. And if I add pi there, I add pi here, and I add pi here. Truth? So I get 0 is less than or equal to 3x plus pi is less than or equal to 2 pi. Is this my B? Is this my C? Yes? So I could have just gone, okay, so here's the amplitude 2. There's my A. And then here's my shift left with 1 period from negative pi over 3 to positive pi over 3. Set that up in my inequality and then just undo the problem and take it back to 0 less than or equal to bx plus c equals 2 pi. So it's an alternative way to look at it if that's something that you would prefer to do. It's part of the theorem for sine wave, cosine wave, and so you can absolutely use it. It's a law. It always works. Okay? Questions? All right, so I'm going to zoom back out here a little bit. And let's look at the next problem. All right, so it says the graph of an equation is shown in the figure. Find the amplitude, period, phase shift, and then write the equation in the form y equals a sine bx plus c for exactly the same conditions as before. For a is greater than 0, so that means that our a is positive. B is greater than 0, so that is positive. And then our c, the least positive real number c. Okay, so that's the same positive c. So that's the same small shift left. So same conditions. And I'm going to work this from 2 angles just like I did the last one. And we'll go in the same order as we did last time. So let's start with the amplitude. From the midline is the x-axis to the peak. We have a distance of, or an amplitude of, 5. And since our a is positive, we can say a equals positive 5. So there's that. Now I'm going to pick up my pen, my blue pen, and I'm going to identify, I'm going to scoot the page up a little bit. One sine wave shifted just left of the graph. So would you consider this to be a starting point of a sine wave? Yes. If we go from 0 to peak, back to 0, back to trough, and then back to peak, there's one sine wave. Shifted the shortest amount left possible. So what is this value here? It's not 1. It's negative 1, right? And then here it is 3. And so the distance between them, the absolute value of negative 1 minus 3 is 4. So that's my period. It has a period of 4. Okay, so that's what I'm asked to do. So period is equal to 4. And if we're going to find B, we use the formula for period that says 2 pi over, in this case, it's a positive B, so we don't need absolute value. So 2 pi over B actually equals the period of 4 that we found. And now we just need to solve for B. Any questions about that? So I multiply both sides times B, and I get 2 pi equals 4B, and then divide by 4 pi over 2 equals B, right? Because we simplify pi over 2. All right, so there's our B term. And then we'll switch to our green pen, and we'll look at our shift left. So here's our shift to the left. So that's a shift, a phase shift. Left 1, or negative 1. So there's your phase shift. Left 1. So our phase shift is negative 1. And to find our phase shift or to find our C term, the formula for phase shift is the opposite of C over B. And our B term is pi over 2. Truth? And our phase shift is negative 1. So we'll take our actual phase shift and the formula for phase shift to find our C term. So how do you think we're going to clear that fraction? Multiply both sides times pi over 2, right? So that's negative C equals negative pi over 2. And then, so C equals pi over 2. Okay, so we write our equation. Y equals our amplitude, A, sine of B, which is pi over 2, x, plus C, pi over 2. And there's our equation. And then again, remember that I told you that we can create the B and C by using our formula that we've used before to do phase shift and period change at the same time. So if you don't mind, I'm going to just come over here where I have a little room to work. So one full cycle of our shift left, our period started at negative 1, less than or equal to x, less than or equal to 4. And we want to get this back to 0 on the left and 2 pi on the right. So what would we do first? What do you think we could try? Add 1? Add 1 and add 1. Oh, that's not a 4, it's a 3. Check my math, people. That's a 3, not a 4. It's a distance of 4. Check that. All right, so that gives us 0 is less than or equal to x plus 1 is less than or equal to 4. All right, so the left side I have what I desire. I have a 0, but on the right side I have 4, and I want it to say 2 pi. So how the heck am I going to change this 4 into a 2 pi? I'm going to multiply it by something. So something you could do is say, all right, I'm going to take 4 times some number, and I want it to equal 2 pi because I really want this to say 2 pi. I could solve that for x, don't you think? Yes, 4 times what number equals 2 pi? This is what I'm looking for. Divide by 4. X equals pi over 2. All right, so that means I'm going to multiply all 3 parts of this equation, or this inequality, by pi over 2. So I'm going to do by pi over 2. So pi over 2 times 0 is 0. Pi over 2 times x is pi over 2. X. Pi over 2 times 1 is pi over 2. And then pi over 2 times 4 is 2 pi. And there I have it, back down to the full cycle of a sine function without any phase shift or period change. And there is, you see it, your B term and your C term, just an alternate way to get there. Something that I would suggest that you do as you're working the problems, I'm assigning you 4 problems like this, so 2 like example 1 and 2 like example 2, is to just go into Desmos. And so for here, if for example, I have the equation of the first problem that we found, but here's what I want to, I'm going to actually throw it out and start over. Okay, so over here in the settings, what I like to do in the settings is I like to make sure that the scale of my graph matches the scale of the graph that I'm actually evaluating. And so this right now the projector or the calculator's in radians, so that's good. And my x-axis starts at negative pi. Could you check that graph, the first graph on your paper? Does it start at negative pi? And then it stops at 3 pi? And would you agree that the step on that, it has a mark at every pi over 2? So I can actually set the window to look however I want. I can make it match the graph that I'm looking at. And then does the y-axis start at negative 3 and stop at positive 3 with a step of 1 or a scale of 1? So then once you make the scale of your graph match the scale that's on the graph that you're evaluating, you can type in your equation. So as y equals 2, sine, what was it? X, what was it? 3x plus pi. And then you can just look to make sure that, look at this. Do you see that? Negative pi over 3. That's the shift left pi over 3. And pi over 3, look at that. And it'll give you all your zeros. You can use Desmos. It's so helpful. Does it cross at pi over 0? Check your graph. So you can see that as you cruise along, what's nice is when it's set in radians, it'll give you exact answers. And you can verify that the equation that you wrote actually produces the graph that you're evaluating. And then you can do the same thing, of course, for the other example by changing the scale on your x-axis to go from -5 to 5 and a scale of 1 or however it's worked out there. Okay? Questions about that? All right. Then here I have one just miscellaneous problem thrown in your notes that doesn't have really anything to do with the writing the equation of sine waves, but I didn't want to have one note page with just one problem on it. So a little application and then we'll be done. So here's the problem. It says the height of a tide at a particular point on the shore. So the height of the tide. Okay, you're thinking about what tide is? You know how it's controlled by the moon, right? All right, can be predicted by using the 7 trigonometric functions called tidal components of the form y equals a cosine of b times t, t being time, plus c. The principal solar diurnal component may be approximated by the function of time is a cosine pi over 2t minus pi over 12t minus 7 pi over 12. And you're asked to sketch the graph of the function if the height a is 0.2 of a meter. Okay, so you want to sketch a graph. You have the equation. You have the amplitude. You should be able to use the amplitude, the period, and the phase shift to sketch this graph. All right, so let's start with rewriting the equation. F of t is equal to plugging in our 2/10 cosine of pi over 12 t minus 7 pi over 12. And let's find our amplitude, our period, all of that good stuff. So I'll start with A. Our amplitude is 2/10. Okay, we got that. Our period. So to find the period, we take 2 pi, right? And divide it by the absolute value of our B term, which is positive. So pi over 12. And we'll solve for, we'll simplify that. So I could write that as 2 pi times 12 over pi. Do you agree? Cross simplify our pi's. And we get a period of 24. This is tidal components, 24, and 24 is part of the time. What do you think that represents? 24 hours? Oh, 24 hours. That makes sense. Okay, so a day. All right, now all we have to do is find our phase shift. So I'm going to quickly do that, grabbing up my green pen here. I'll work it over here. So my phase shift is the opposite of C. So that would be a positive 7 pi over 12 divided by B, which is 11 pi over 12. And that creates a complex fraction, but what's nice is the denominators match, so we can cancel those. Truth? And 7 pi over pi is 7. So it's a phase shift of push the graph right 7 hours. Basically, that's what's happening. Okay? So if I design a graph that's representing this information, I'd probably give it a title. I definitely give it a title of the principal solar diurnal component. So I do that. I'd give it a title because this is what you do when you create a visual for a graph. And then what does our y-axis represent? Y-axis is amplitude, and the amplitude is measuring the height of the tide. So we would put this is the height of the tide. And what do you think when the tide is at equilibrium? What's the equilibrium represent? The average tide? Think it's sea level possibly? Could be sea level. So this is the height of tide in meters. Okay, and you know what? I'm going to actually stretch this graph out a bit because I'd like to go over a long period. Because I have a 24-hour period that's being shifted to the right 7. So I'm thinking I've got to go all the way out to 31, right? 24 plus 7. So I've shifted graph right. So I think I'll go ahead and put 24 here. And this is going to be my time. And I don't know if it's my time since midnight or my time since noon. So I can't be super specific about what the time, like the starting time represents, but we'll just call it the time. All right, and then let's cut that in half. Now, since it has a period of 24 hours and it's a cosine function, I could divide that evenly into 4 sections, right? So that I can get a high, a 0, a low, a 0, and back to a high. So I think we'll cut that in half to 12 hours. Then we'll cut that in half to 6 hours and 18 hours. And I'll just go ahead and put in my amplitude here of negative 0.2 or 0.2 to 0.2. And since it's a cosine function, we know it starts up at high tide, right? At 0 hours. And then it hits equilibrium at 6 hours. It hits low tide at 12, back to equilibrium at 18, and then up to high tide again at 24. Now, this would be the graph of our function if we didn't have a phase shift. Everything's shifting to the right 7. So basically, I'm going to go past 6 o'clock to 7 o'clock, and now it's high tide because I'm shifting everything to the right. So 0 at 7 a.m., maybe if this is starting at midnight, at 7 a.m., that means it's high tide, or 7 p.m. if we're starting. Just depends on the starting hour. So if I'm taking this point that's at 6, this equilibrium time or sea level time, and I push that 7 hours forward, I'm at 13. So hour 13. So that'll be 13. I'm going to go ahead and put a 7 here. And then if I take this low tide at 12 and I push that 7 hours forward, I'm at hour 19. And then if I take this equilibrium at hour 18 and I push that 7 hours forward, I'm going to be at hour 25, which basically means I'm at the next day. Truth? And then I'm going to take this 24 hours. I guess I better go out here to 30 hours and push it past 30 hours to 31 hours to get back to high tide. So my graph would look something like this. And there was an explanation of the graph and analyzing the data, talking about what it meant, okay? And so on Canvas, there are 5 problems that you're going to be solving that are very similar. You'll find them in assignment 9.1C. Just do the whole assignment.